All right, let's start the new section, section 4. We're gonna continue talking about regression, and it's gonna be two different types of regressions or extensions to the previous simple regression model. The first extension is multiple regression model, where we're just gonna have more than one predictor variable x, and another one is logistic regression, is the regression when variable y is not a continuous variable, but it's a 0, 1 variable or discrete variable in general. Um, all right. So we'll start with a few basic concepts. Many problems involve more than one predictor variable, and even when we talked about Zillow example, the home prediction problem, our data set had multiple columns in it, but we just decided to use the living area of the house just for convenience. But in general, we can use pretty much all of the predictor columns that we had in the table, because you might imagine that number of the bedrooms does change the price, the location of the house does change the price. So there are multiple factors that can affect the output variable y, and we need to account for them. Another example is multi-factor asset pricing model, APT, when you try to calculate the stock returns, and they will depend on multiple market factors. If you try to predict demand for a specific product, then besides just dependency between demand and price, there are also advertisement campaign and other attributes might affect what demand you'll generate for this product. And finally, the internet analytics, when you try to predict behavior of your customer on your website, there are multiple attributes about this customer. And we talked about the Netflix example. So they try to learn multiple different hidden features about who their viewers are in order to understand what type of movies they're going to like or dislike. The commands are the same, so you've seen those commands before. So the command lm is just the command that builds linear model, and the command glm, generalized linear model, we're going to use it for logistic regression a little bit later. And the extension of the lm model for multiple linear regression, when you have more than one predictor, instead of just saying y tilde x, you say y tilde x1 plus x2, where the x's are just prediction variables. So in R they call it formula. So you basically say, what's your mathematical formula describes relation between x and y look like, and you can add things to this formula. You can say, for example, product of x1 and x2 also affects. So you can add x1 star x2 to the formula. The diagnostics is the same. If you ask to plot Cook's distances for the model, it will do it. Or if you just do plot of the model, you'll see the same diagnostics plot as you saw for the simple linear regression. And the predict function works the same way. Predict.lm, you specify which model you want to use for the prediction, and you specify what's the new inputs x that model needs to predict for, and it will generate the output y, or multiple outputs y if you have multiple vectors x to predict for. This is a general relationship between x and y. You remember the names from the previous set of slides. Y is called response variable, outcome variable, or in other words, dependent variable. And x is called either exploratory variable or input variable or predictor. Another word for it, predictor. Or we can just call it, actually that's it, predictor, explanatory variable. Yeah, so those are the names that people typically use for those. And the general relationship between y and axis is that it's just this function f. So it's, you can imagine it's just some box where function f lives, and it takes inputs x1 all the way to xp, and it produces what we call y hat. And of course, f is just model of the real relations between x and y. So it's not perfect, and the fact that it's not perfect, we just add this error term. So we say that y equals y hat, so that's what predicted by the function. and plus this error term. So the error term tells us that the model isn't perfect. And the linear version of this model is just, it's a linear equation, right? So y is linearly related to p predictors, and we use, again, beta 0 for the intercept, and beta 1 through beta p to denote the slopes associated with each of the p predictors. So we have p predictors in this case. The assumptions for the multiple linear regression model are similar to the assumption of the simple linear regression. So first thing is that relationship between y and each of those predictors have to be linear. And you can check it by just looking at the scatter plots. If you are plotting scatter plots. So in this case, you will have p scatter plots for each input variable. So you'll have one for x1 and y, one for x2 and y, and all the way to xp. And what you want to see is you want to see this linear looking relationship between each of those predicted variables. And if you see something like this, right, then again, you might be able to solve it with transformation. So you might be able to apply transformation to this specific variable and put the relationship back to linear relationships. So that's first assumption. X's and y has to be linearly related. And the next assumption, again, that the errors should be normal. So if you look at your, if you plot y minus y hat, so let's say you have training data. So training data is just the table that you use to estimate the parameters of the model, right? And it's a sequence of pairs, y, x1. Now x1 is a vector here, so instead of being a single number, it's a vector of numbers now, right? So y1, and then you have all the way to n training points. And here I'm using this script in the top part, so I use it as a superscript to index the training data point so that we don't confuse with the predictor. So predictor on the script will be used to denote the predictor. So each training point, is a row in your training data set. So you can imagine you have a big training data set, and each row is the observation or a training point, and each xj is column. So you have usually y would be your first column in your table, then you have x1, x2, x3, all the way to x5, pi, p, and then you're going to have all the observations as rows in this table. Now, if you look at all this yi minus yi hat, so you take the ith observation and you do the prediction for this ith observation, you get this y hat from the model, and you look at the differences between y and y hat, then you plot histogram of it, so you do the histogram of these, then you should be normal looking histogram. Should look normal. So basically it should look like a histogram, so that if you imagine drawing a bell curve on top of it, bell curve would be a good description of the histogram. So it should be symmetric, should not have heavy tails on either side, and should be quickly decayed. So it's you remember this bell curve has this exponential decay from the center to the tails. All right. So when we talk about coefficients beta, there are a couple of things that we're interested in. We're interested in the statistical significance, and statistical significance tells us whether there is a relationship between specific predictor and output variable y. So we do the same thing. We always check for the hypothesis that coefficient beta j equals 0, and alternative hypothesis is beta j not equal to 0. And for this hypothesis, it means if the null hypothesis is true, then that means that xj, the jth predictor, and the output variable y are not related. Means that it might be the case that the true value of beta j is 0. So maybe we should not be using this predictor at all. And usually the procedure is just to remove this predictor from the model. And the way we're going to check it, again, by looking at the p-value. And again, it depends on which field you're in, but typically p-value, which is greater than 0.05, will tell us that the null hypothesis is correct. So if this is the case, then we say null hypothesis cannot be rejected. Meaning that we do not have enough evidence in the data to tell us that x and j and y are actually related. So this is called statistical significance. Statistical significance, whether the true value of beta j is 0 or not. And again, we're going to look at p-values or t-ratios, whatever you prefer. And the next value is what is called economic significance. And economic significance is just the magnitude of this coefficient beta. And you remember in the simple linear regression, the slope coefficient beta was measured in the units of x divided by units of y. So is this actually vice versa, units of y divided by the units of x. Here is the same thing. Units of beta j are units of y divided by the units of jth predictor, xj. And so beta j tells us by how much y changes on additive scale if xj changes by 1 unit. Okay, and the size of this change is called economic significance, or also sometimes called marginal effect. So marginal. Just a fancy economic term for something that is relatively simple. Okay, and the diagnostics of the model is actually done in a very similar way as we did with simple linear model. You're just gonna do plot model, and now R will give you 4 plots, and 4 plots. The first one where you can look at the residuals, whether they are normally distributed. Actually, first plot and the second plot. The second plot will give you the QQ plot, and the first plot is just residuals versus the fitted values. And then 2 other plots will show you the leverage point and also another residual plot. So essentially, we mostly care about 2 plots out of those 4. One is for leverage point, and another one is to detect whether the residuals are normally distributed and whether they're outliers. So you actually can look at just 2 of the plots from those 4 to make conclusions. And so there's one more thing to keep in mind, that multiple regression does take into account the correlation between the factors. It might happen that your predictors might be correlated. Linear regression just takes care of that. It does all the work for you. And also one thing to keep in mind, you might, once you have multiple, so somebody comes to you and gives you a table, okay? And one of the columns in this table is variable y, and the rest of the columns you might use as predictors. And you, quite often, you don't really need all of those other columns as predictors. Sometimes people just give you relevant information. And it's actually hard to say which columns to use for predictions and which are not. And the process of identifying specifically which columns to use is called model selection. So process of model selection in a more simplified is which columns to use to build a model. So which ones to include, which one not to include into the model. And so usually you will do it through some experimentation. You'll try, a few of those which you assume are trivial or obviously should be related to Y, and then you start adding the other ones which intuitively is not clear whether they're related to Y or not. And what might happen is, for example, you add 5 variables into your model, so you have 5 predictors, and all of them significant, and then you add the 6th one, and one of those previous 5s become insignificant. So the relationship between predictors also affect how one appear in relation to the Y, whether it appears significant or not. So we'll so also keep this in mind. So the p-value always can change when you change number of the predictors that you include into the model. And again, the common sense is if variable never seems to be significant, always has those high p-values, just throw it out. And again, if you use model for the prediction, then you should care less about the p-values, and maybe you should care more about the predictive power. So you look at the size of the residuals, and whichever model gives you the best prediction, you basically take it regardless of what type of p-values you see there.